So good afternoon, everyone, and thanks for joining us. This is our lecture on of the IEEE SMC Society. So before starting with our speaker today, which is Professor Tommaso di Noia, I would like just to briefly introduce our society, the IEEE Systems and Cybernetics Society. So, as you know, the SMC Society is part of the IEEE, which is the world's largest technical organization. In particular, our society is composed of three different research areas. So systems, humans, and cybernetics is one of the, it's probably the unique society of the IEEE that try to merge these three different areas. In the last 2 or 3 years, the number of members of our society doubled. We passed from 4,000 people to almost 7,000 members. As any other society in the IEEE, the SMC Society publishes several magazines, transactions, and journals, and also organizes several events. Later I will show you some of the most recent call for papers. To join our society, you must be an IEEE member, and the cost to join the society is very, very low. It's just $9 for IEEE member and $1 for the student members. Regarding our chapter, so I am the vice chair of the Italian chapter of the SMC Society, and Laura Giarre is the president. Last year, our chapter won the IEEE Italy Award for the most increased membership award, since we increased the number of members in our society and in our chapter. This is also thanks to several events that we organize each year. In particular, this is the second year that we organize the Early Career Researcher Award. So we give an award to a young researcher. This year, the award has been assigned to Dr. Claudio Savaglio from the University of Calabria. Now, some of the events that the society is organizing, as you probably already know, the flagship conference of the society is the IEEE Systems and Cybernetics Conference. Next year, this conference will be organized in Washington State at Bellevue in the first week of October. So there is still time to submit papers and to organize special session in the flagship conference of the society. Another important event is the Conference on Human-Machine Systems that will be held in Singapore in July, in the first week of July. The deadline is quite near, it's at the end of this year, so 30 December. Another conference that we are organizing, and so it's also sponsored by our chapter, is the Smart World Congress that will be held in at the University of Calabria. The conference will be from 7th to 11th of September, and the deadline for submitting paper is the 1st April of 2026. Some other events are COGSIMA, so the conference on cognitive situation management that will be organized in Arizona at the Arizona State University. The deadline for submitting papers already expired, but there is still time to register and to attend the event. And lastly, we just give our technical sponsorship to this event, the IEEE Conference on Cyber Humanities that will be held in Venice, again at the beginning of September. And so, as you know, as part of the events that our chapter organizes, we have this lecture series. Today, we have the honor to host Professor Tommaso di Noia. Professor Tommaso di Noia is a full professor of information and data management at the Polytechnic University of Bari. His research focuses on artificial intelligence and in particular also on recommender systems. And recently he's also working in trustworthy AI with attention to machine learning, explainability, fairness, and privacy protection applied to these recommendation systems. Today, I will talk about the standard practices for data processing in recommender systems. So, Professor Di Noia, thanks for joining us, and the floor is yours. Thank you.
Thank you very much for this invitation, and thank you very much for having me here today. Okay, I've just shared my slides, so hopefully you are, you can see them. Okay,
Yes.
so yeah, okay, so today we will try to go through this standard practices for data processing in recommendation. So we will start by, just by giving a thank to the contributors of this topic. So the guys and girls who are currently working on this topic in our lab. So thank you very much to Alberto, Matteo, Angela, and Daniele for their contribution on the topic, and also on the development of the tool that I'm going to present at the very end. So what happens in recommender systems? Well, as in many machine learning based systems, so we have an evaluation pipeline which is often an offline evaluation pipeline. And as for this pipeline, we know that we have this main 5 steps. So what we have is that, okay, we select our dataset, so we have the dataset selection, then we somehow process the data, so we try to clean, we try to split, we do something with the data, and once we have this data well prepared, then we inject this data within our algorithm to train it. And once we have the final trained model, we use this model, at the inference time, so to compute recommendation. Once we have the recommendation computed by the final model, then we are able to evaluate it. So these are the main 5 steps within the typical evaluation pipeline in a recommender system. What happens is that if we do not carefully take a look at the first steps, very small changes may dramatically change the overall behavior of the algorithm, and then if you change the overall behavior of the algorithm, then you are also changing, what is the evaluation of the algorithm itself. So that there is no way to have a kind of reproducible results about what you already produced before and then you published on your paper. So this is what we need to consider today, and especially we will see that we will focus on the first 2 steps in this pipeline, because they are very underrepresented in the scientific literature, but we will see how important they are when we train our model, and then and especially when we evaluate them, whenever we want to have a fair comparison on the results, which is at the basic of our scientific evolution, and especially if we want to reproduce the results that we present in our papers. The point is that over the years, there has been a lot of attention on training, recommendation, and evaluation. You can find tons of papers talking about, how to train, how to tune hyperparameters, how to do this and that in the training phase. Of course, we have a lot of papers on the recommendation part, selecting the best algorithm, identifying all the different metrics that you want to measure, that you want to optimize. And the same is for the part of evaluation. But a very low attention has been paid to the dataset selection and the pre-processing part of this pipeline. So that's why this is where we are going to this is what we are going to discuss today. And so we will start by discussing best practices for data selection, and then we'll move on to the data processing step. Well, of course, this becomes even harder if we consider that, very often in a recommendation scenario, what we have is that the dataset basically contains, collaborative information. So it contains interactions between users and items. So we have these collaborative signals within the dataset. But what if we add more information to the problem? So what if we add multimodal signals to the problem? What if we add text? What if we add descriptions? What if we add images, videos, and audio signals to the data set that we want to process, and then we want to use to train the problem? So these are all elements that we need to consider in our overall pipeline. Okay, so let's start with a very basic, basic notion. So hopefully we know that a recommender system is this kind of system that is designed and trained to under the assumption that we can somehow get from the data all the user preference patterns, and then based on these patterns we can at the end predict something new to the user. Okay, so something that the user could be interested in the near future. So something that has not been, let's say, watched, a movie that has not been watched yet by the user, a song that has not been listened by the user, and so on and so forth. Okay, so that's why once we have this algorithm, so we need to evaluate how good is the algorithm, how good is the model in recommending the best items to the users given the user preferences. So if we look at the reference handbook that we have in our field, so if we look at the Rexis handbook, so as for the evaluation part, the handbook distinguishes three basic settings. So we can have offline experiments. So we can have our data set, we can crunch the data, and once we have all this data crunched, then we can train the model and then compute the recommendation, evaluate them. We can also use user studies when we involve people in the evaluation of the recommendation results, or we can also have online experiments where we do some kind of A/B testing to evaluate the final approaches. Well, of course, we easily understand that offline evaluation and offline experiments are the most widely adopted solutions that we use because it is easier to implement them. It is easier to run our experiment more than once, and if something goes wrong, then we can just go back to the first step and start again. So that's why this is something that is very present in our papers, as also been shown by this recent survey by Christine Bauer, Eva Zangerle, and Alan Said, when they show that basically by looking at the papers published in the last years on the topic on recommender system, the 72% of the papers they use offline evaluation, and the 60% of all the approaches analyzed, they only use offline evaluation. So that's why this is something that we need to look at very carefully. So what happens with offline evaluation? Well, we have training and test data coming from user feedback, so coming from the interaction of the users from a specific system. So we know that, for example, we have data from Netflix, we can have data from Amazon, we can have data from other, from Spotify, or from whatever platform that you can imagine when you have a user exploiting and using the system itself. And a very good point with in favor of offline evaluation is that once we have this offline evaluation, we assume that it is easier to compare different results. Since we have an offline evaluation, so we assume that we can reproduce what has been presented in a paper as an offline evaluation. And once we have reproduced this evaluation, we can compare the final results with those that we have. Of course, this can be done only if we have available public data sets. And, as for the recommendation scenario, we have many of these data sets. I will tell you something about them in a few slides. But among the most famous, we can for sure mention those released by the GroupLens group. So, for example, MovieLens is one of the most used and adopted data set when you look at Rexis paper. And the same is for the data set released by Netflix for the famous Netflix challenge, which gave a big boost to the field in the at the end of 2000. At the beginning of this century, basically. And then we have data set from Amazon reviews, which is a very rich data set containing interactions, reviews, and many other interesting information. But also we are getting nice data sets from Chinese companies. So for example, Chinese and Russian companies. So for example, both Yandex and Alibaba are releasing data sets for our experiments. But the point is, let's start from this dataset part. Once we have the dataset mentioned within a paper, we have different ways to refer to this paper within the text of the paper. Okay, so we have a good way, we have ways that are okay, but we also have completely wrong and bad way in terms of, again, what we want to do, in terms of what we want to reproduce. Usually, these data sets are released publicly, so you basically have a CSV file, or you can have a zip file, and you can download this file and process and use it. So when you use this data sets within your paper, you should refer to the data sets itself, so to the URL where you can get the paper, or you should refer to the paper that introduces this data set. But the point is that this is not always the case in many papers, because sometimes we have this, sometimes we have a reference to a pre-processed version of this dataset that has been used within the paper. But we also have situations where there is no link at all, but just the name of the dataset. So in this case, it is very hard to reproduce everything. So in order to give you an idea on how the selection of and the correct referencing of a data set is important in this field, I'm just showing you this example that somehow is the example from which we started our investigation on this aspects of the recommendation problem. And this is related to the GoWalla dataset. So what happens, this dataset is a very rich and important dataset in our community. It was published originally in 2011 by this very active group in the recommender system community. And it contains a lot of information about the social network, and this information are basically location-based interactions between users and locations. So you have check-ins basically, and you have plus than 6 million check-ins. So it is a very rich data set, and this data set originally has been released as two data sets, a friendship network and the collection of users check-in. So you can put everything together if you want, or you can also use the two data sets in a separate way. So now this is the example. So why this data set is popular? Because at a certain point it was used in a paper proposing a very important and famous recommendation algorithm, so light GCN. It is a graph-based convolutional network approach, to recommendation. And then, starting from this paper, the data set started to be very, very famous. So now imagine that we want to reproduce the experimental setting presented in this original paper. So if we look at the paper, what we see is that, okay, to reduce the experiment workload and keep the comparison fair, we closely follow the settings of the NGCF work. Okay, so this is the setting of another work. So in order to refer to the version of the dataset and to the way the dataset was pre-processed, so these authors, they refer to another paper where they did something with the dataset. But what was the work done by this author? So let's continue our investigation, and then we see that there is a connection and a cross-link to different papers saying, okay, I did this, I did that, I did this kind of 10-core setting, for example. But in other case, we read, okay, but we consider a minimum of 20 check-ins, which is indeed is in conflict with what was mentioned in the other paper. So if we follow these links in order to understand what is the actual data set, what is the actual data that I need to process if I want to reproduce this paper, well, it is not an easy task. And sometimes you completely get lost because you cannot understand what is the actual data you should work with. What happens is that very often they refer to a data set, but at a certain point they apply another filtering strategy. This is just to show you what is the final result that we got when we try to say, okay, so let's see what is written within the paper and let's try to reproduce, starting from the original data sets. Let's try to reproduce the number of users, the number of items, and the number of settings of ratings. Sorry, in the different papers. So here in the first row, you can see what is the original GoWalla dataset. So you have this number of users, you have this number of items, and this number of ratings, and the minimum rating per user is 1. So this means that you have you cannot have a user having one rating, so having rated just 1 item, 2 items, 3 items, or more. And then we see what happens in the Expo matrix factorization paper. So they declare that they have based on their splitting and everything else, they declare to have this subset of the users, which is fair enough. You know, it makes sense because they say, okay, but we have this number of users and this number of items and this number of ratings because we filtered the data by using this strategy. So we were only interested in users with at least 20 ratings, so 20 interactions. This is just to avoid cold users, so to avoid cold start situations, which usually need to be managed in a different way. So what we did at a certain point was, okay, let's try to reproduce this data set. So let's see what happens when we consider exactly what we did. And what happened was that, okay, by looking at their data set, by looking at the data that they released, we had exactly the same number of users, we had exactly the same number of items. Well, we assume that we have exactly the same number of ratings, but what happened is that when we reproduced everything, the actual minimum number of ratings for each user was 1. So it was not the one declared by the authors. So this looked quite strange. Well, of course, if we want to reproduce our experiments, you have this QR code here that it gives you the opportunity of reproducing everything. And the same is for this other paper, the one proposing the NG-CF approach, where also in this case they said, okay, we declare that we're using we are selecting users having just at least 10 ratings, and these are the numbers. And again, we reproduced exactly, starting again, remember, from the same original dataset. We started to reproduce what they did, but the numbers were completely different. So for us, it was impossible to reproduce their paper, and for us, it was impossible to actually compare with their results, so with their approach. So since we were proposing a new algorithm, it was impossible to compare with the actual results that they presented in their papers when they presented for the first time the two approaches. So that's why we know that reproducibility as a very important role. So over the last years at the Rexis ACM Rexis conference, we have a devoted track for reproducibility. So we have papers that reproduce other papers just to see if everything is still there and everything can be actually reproduced and give a scientific advance to the field. But what happened is that we have this very interesting papers where they show that most of the papers cannot be reproduced because they have many flaws in the way they present their experiments. And this problems is even bigger when we consider side information. So we consider not only interaction, so we do not consider just collaborative information, but when we consider also, as I was mentioning before, reviews or, for example, images or the videos and everything else. Well, this is just two papers by two different groups, but we are both in Bari. The point is that in these two papers, what we do is to present in a clear way and to publish in a clear way data sets such that we have the original data set containing only collaborative information enhanced with side information. So enhanced with information coming, for example, from knowledge graphs or coming from multimodal information. So these are steps that we need to do if we want to foster reproducibility in our field. And this is something that has been done also by other groups. For example, the group releasing the Amazon reviews dataset is very active in this respect, and the same is for the for the group releasing movie lens, or the group lens group. So we need standardization already in this initial phases. So without standardization, we need to re-implement always the same algorithms. We have different pipelines that lead to different results. We cannot have interoperability because we don't have shared pipelines. And since we don't have shared pipelines, we cannot customize these pipelines for different experimental settings. And we know that if we don't have if we don't have the validity of these pipelines to be checked, so we cannot share them. So that's why, let's talk about data handling and processing in recommendation research. So we know that in our in a recommendation problem, it is not possible to identify unique data processing steps because the recommendation problem is quite a multifaceted problem. So depending on the problem that we want to address, then you may have different different steps. But let's see if we can find some general, at least, approaches. So a general pipeline that can lead us in this steps in this processes. So that's why we surveyed some papers from top tier search and recommendation conferences. And what happened sorry is that we selected this 79 distinct data sets by serving this 55 papers. So what we realized was that each paper introduced more than one data set, and this data set was not used in other studies. So this was a high heterogeneity in the recommendation data sets when we talk about offline evaluation. So among these data sets, these are the most popular, and these are the data sets that have been used in at least 3 papers. So we have this Yelp data set, we have the Amazon books, beauty, toys and games, clothing, and and other data sets from the Amazon group. So we have the movie lens data set, we have the Last.fm, GoWalla, Tmall released by Alibaba, we have the Yelp data set, we have another data set released by Alibaba, and so on and so forth. So we also have data sets coming from websites that do not exist anymore, such as the Opinions data set. So let's quickly go through this data set just to give you an idea of the heterogeneity, also in this case, of the kind of information that is represented there, and also not just the, let's say, the domain that they describe, but also the way they are they are presented. So the syntactic nature of this data set. So for Yelp, you may know that this data set contains information about businesses, and you have that user feedback are stored as reviews. So this is a typical record from this data set. So you have a review ID, a user ID, a business ID, you have the reviews, so you have the stars here. Then you also have some other feedback from the user, and this is the final review, and of course you also have a timestamp. We have something analogous with the Amazon reviews dataset, which is this which is this set of datasets released by the University of California, San Diego group. They started in 2013, but they are continuing updating this datasets. And currently, the whole data set is divided into 26 categories that can be seen as different data sets if you want to work on a specific domain. This is the way you have the data represented. So you have a user ID, you have the ID of the Amazon category for the item that has been has been reviewed. You have a rating and you have a timestamp, and then you have movie lens. Also for movie lens, you have this you have movies rated by the users, and in this case you have even a new format for your data. And the same is for Last.fm. For Last.fm you have music, and also in this case you have user preferences. And for example, for Last.fm you have this this attribute, which is weight, that is just giving us the number of time the user has listened to this artist. Okay, so also in this case you have other kind of information that can be exploited for a recommendation task. Then the Tmall dataset released by Alibaba, which mainly targets B2C platforms, and also in this case, it has been released as an open data set, for the recommendation community. Okay, I don't want to tell you anything about the Gowalla data set. Also in this case, we have the two data sets that we mentioned before, and the iFashion, also in this case, released by this Chinese company. The very important part here is that you don't have just collaborative signals, but you also have images, you have text, you have different modalities that you can exploit to run your to train and to run your algorithm. And finally, we have these opinions. This opinions collects data coming from a website that is no more active, opinions.com. And, it contains general consumer reviews, general consumer reviews. And in this case, you can find within this dataset what they call trust relationships between the users of the platform. So in this case, what you have is that, okay, I have this trust from this node representing a user, for example, to this other node representing another user. So this means that what we have here is a kind of graph-based representation of the data set. So again, different data sets covering different domains, but also containing completely different information. Well, of course, having so many data sets means that, okay, the field is really mature, and it is very active. And at the same time, having this heterogeneity within the data sets and the data means that okay, there are a lot of different problems that need to be solved, depending also on the domain that you are covering. But this if we want to start to make some order in all this sort of chaos, so we need to first of all, understand how to refer to this data set. So how to refer in a precise way to these data sets. And from our survey, what we got was also in this case, quite different, quite not a homogeneous situation, because we had that 63 in 63 papers we had that they mentioned the original data source. In 58 paper they proposed the copy of the original data set. Sometimes this 27 papers they mentioned the original paper presenting the data set. In these three papers, they refer to a paper referring to another paper, but then we also have cases where we don't have any reference at all. Or, unfortunately, we also have cases with broken links. So we started to say, okay, what is the right way to reference data sets in a correct way? So what we need to do is to reference the original data source. This is one of the best ways to refer to the original paper and to foster reproducibility of our approaches. Another way to correctly reference the paper could be that of citing the original paper. So usually when you have the original paper introducing the dataset, there you have all the information that you need to get, to manage, to process, and also if you want to release a new version of that dataset. So in this respect, we are quite happy because we saw that half of the papers that we surveyed, were referencing the dataset in a correct way. So these are just a couple of examples in this case. So you have a reference to the original paper, or you have a reference to a link to the dataset itself. Well, unfortunately, there are authors sharing a copy of the dataset, and this clearly undermines standardization. So if you share a copy of the dataset, you are creating a new, let's say, a new branch for this dataset. So you are creating new headaches to practitioners or to researchers that want to reproduce your work and compare your work with other works. Okay, and this is a typical case. Okay, where they are releasing a new version of their data set. And again, also when you release a new version of this data set, then you need to pre-process again the data set. So there is always something missing. Well, of course, we do need to avoid these situations where the data set is not retrievable. So if we cannot access to the data, if we cannot access the data, so it is impossible to actually evaluate what has been presented in the paper, and it is impossible to compare with the paper. Okay, this was just about the data set. Okay, now let's see what happens at the level of data processing, because once we have the data, we need to process the data before we use them for training the algorithms. So also in this case, in our survey, what happened was that most than the half of the papers that we surveyed, they declared that they had processed data sets. So, they manipulated the original data before using them. Let's see which are the most frequently used processing techniques. So you can have binarization, K-core iterative, K-core user, K-core item, session length, or other techniques. And these are the most popular in the papers that we surveyed. So, but let's take a look at each of them. And let's take a look also on the potential problems that are hidden within these techniques. So binarization, what happens here? So as for example, we saw from some of the data sets shown before, usually what you have is that a potential feedback can be, okay, a like or dislike, good, but you also have stars. You have, okay, I have 1 star, 2 star, 3, 4, 5 stars, or the number of times I listen to a certain artist, or the number of time that I watched a specific TV series, and so on and so forth. Well, in all these cases, what happens is that usually based on a certain threshold, what the authors do is to binarize this data. So up to a certain threshold, this feedback is interpreted as a dislike, let's say, and over this threshold, the feedback is interpreted as a like. Okay, so we start from non-binary data and we make them binary. Okay, so why this is useful? Because in recommendation, it is very important also to study what is implicit feedback. Okay, so usually we have that like and dislike is the most preferred feedback from many systems, and we also know that some systems. So we have an interesting report by YouTube saying that, okay, if you use a scale of 5 to 10 stars, then and you analyze the data and you analyze the feedback left by the users, then at the end you realize that they mostly tend to give one or 2 stars, or 4 or 5 if you have 5 stars, or 8 to 10 stars. So they tend to be distributed on the two opposites of the scale. So that's why making data binary is something interesting, and it is worth investigating. So what is K-core? K-core is another way of processing data. So the formal definition from graph theory of K-core is that a K-core algorithm finds the largest subgraph of a graph where all the nodes have a degree of at least k. So if you look at the example here, we start from this graph and we arrive to this graph on the left-hand side of the slide, where we see that all the nodes in the highlighted subgraph, they have a degree equal to 3. Okay, so in this case we have a three core of the original graph. Well, this approach can be also applied to recommender systems, because at the end of the day, what happens is that, okay, if we see users and items as two different nodes in a graph and their interaction as edges within this graph, then we see that we can represent represent the data set, the user interaction, as a bipartite undirected graph. Okay, so that's why we can use also K-core in this case. Well, actually, in the recommendation community, K-core has been interpreted in a let's say more relaxed way, because the interpretation is that instead of retaining all the nodes with at least k node degrees, we just retain only user items with a node degree greater than or equal to k. Okay, so we're not exactly looking at the k core, but it is enough to have a number to have a degree for the number that is greater than or equal to k. Well, actually, also in this case, and there's a simple preprocessing of our data set, we can make mistakes. So, for example, if we perform a one-shot K-core preprocessing, what we can have is to say, okay, I am removing this item or this user, or this item or this user, because they don't have at least 3 or 4 items or 3 or 4 links. Sorry. But what happens is that after removing these nodes, it may happen that some nodes that we saved before, right now, they do not satisfy the K-core criterion anymore. So they need to be checked again in an iterative way. So that's why a common mistake is that to perform a K-core on user and items in a non-iterative way. Okay, so in this case, well, of course, at the end, the pre-processed data set is not an actual key core dataset anymore. Okay, so that's why we strongly, as a community, we strongly recommend to use an iterative key core approach in order to have a clear representation of the data, in order to have a deterministic selection of the users. When you have sequential recommendation, and then when you have, for example, domains where you have that the sequence of items enjoyed by user is very important, then also the length of the session is something that you need to consider, and that you need to take into account when you want to pre-process your data. So also in this case, you need to consider the length of the session that you want to use for your training. But also in this case, selecting the right length of the session is an open question. What is the right session? Can we just set a fixed length of the session, or should the session refer to the user history, or to to a specific period of time? For example, in Christmas, we are more prone to listen to certain songs which we will never listen to, during the summertime. Okay, so these are all problems that we need to consider when we pre-process data in sequential recommendation scenarios. And then the other point is that of data splitting. So we know that when we train a machine learning system, we need to split data. So we need to have, data for training and data for test. But also in this case, the right splitting is something that need to be clearly defined and clearly stated if we do not want to create inconsistent rankings, for example. So the most frequently used splitting strategies are those that you can see here. So we have a random holdout, a temporally one out, a fixed holdout, a randomly one out, or a temporal fixed. So what happened with the first one? So with the random holdout, this is the most common approach, unfortunately. And I have to say unfortunately, because it does not go into the direction of fostering comparability and reproducibility of results. Because what you have is that every single time you run your algorithm, you randomly split the overall data set in the training and test set. So you don't have a fixed split, and then you say, okay, I have used this fixed split every single time, and for whatever reason. But once you have that split, splitted version of the data set, then you say, okay, this is the version that I've used. If you want to reuse it, and if you want to compare with my results, please do that. So also in this case, selecting the best splitting strategy is still an open question, especially when the splitting strategy also considers time. Because when we consider time, what we can have is that, we can say, the first, let's say, suppose that we have 100, a session of 100 items for each user, and then we say, okay, the first 70% of the items are used for training, the second 30% is used for test, or 80-20. It depends on the splitting that you want to adopt. But this makes sense, but up to a certain level. Because if we look at this representation here, so what happens is that, suppose that we are in 2025, okay? So in 2025, what we want to do is to recommend something new to the user, okay? Even though the history of the user, in November 2025, we want to recommend something new, even though the history, the interaction of the user with the system ended, let's say, in March or in April. Okay, so it makes no sense to recommend something that was enjoyed by the user in April, because I want to do something that is more recent, that is more interesting. Well, then the other approach is that of saying, okay, let's use a global temporal split. Okay, so we say, okay, from this time on, everything is used for test. But also in this case, what happens is that we can have strange situations, because suppose that in this case we have this a part of the user profile used for testing, but also in this case, so what is the good items that you use it for testing? Is it the last one in the session? Is it the first one? Is it just one of the items within the test set? Is something, I want all the items within the test set, or I want all the items in the test set but recommended in the proper sequence. Okay, because for example, in this case where we have all, what we basically have is that this items are considered as a set, so in an ordered set of items, while in this case I still consider an ordering. So again, also splitting is something that need to be clearly stated, and is something that need to be clearly designed when we want to propose something new in the recommendation field. Finally, we have data characteristics of recommendation dataset. So we know that depending on the way data are distributed in our dataset, we can have different results. So the same algorithm may perform in a completely different way depending on what we call the data characteristics. This is something that was for the first time proposed and analyzed by a seminal paper by Adomavicius, Geda Adomavicius and Zhang in 2012. And they show that, depending on this data characteristics, the final performance of the same algorithm, exactly the same algorithm, the same splitting, same everything, but the performance, they change completely. And this is this is something that we also added to this topic, and then we said, okay, well, if we interpret recommendation data as a bipartite graph, so also these characteristics can be extended to see, okay, let's take a look at the topology of the graph, and so let's see what happens when the graph has certain characteristics. So we don't look just at the matrix where we have users and items, but we also look at the graph generated by this matrix, and we look at topological characteristics of this graph. And what we showed is that, okay, also these topological characteristics, they influence the final result. These are just the elements that we use when we compute the data characteristics. So the user set, and then the number of users, the item set, the number of ratings, the number of a neighborhood for each user, the number of items for each item, and also the second order neighborhood, both for items and users. Okay, and this is specifically interesting when we look at the graph-based version of the data set. So let's consider this structural characteristics, that is the space size. The space size is just the product of the number of users times the number of items. This quantifies the total number of potential user item interactions in the dataset. This is one of the characteristics that we need to consider, and we need to explicit when we present some results relating to a recommendation approach. The other structural characteristic is the user item ratio, that gives me an information about the proportion between the number of users and the number of items. And of course, when this value is equal to 1, it indicates a perfect balance between users and items. The final structural data characteristic is what we call density or sparsity. Okay, so if we have a very dense matrix, what we expect is that there is much more information encoded there, and then it is less difficult to make recommendation emerge from this data. But we can also look at the distributional characteristics as those referring to the Gini index, and also in this case, the Gini index is telling us information about the inequality in the user or in the ISM frequency distributions. So if I have a Gini index equal to 0, what I'm saying is that I have a perfect equality in terms of, for example, history length for user or number of ratings for items. So if I have a Gini index equal to 0 when I consider, for example, items, what I'm saying is that, okay, all the items has exactly the same number of feedback. And the same is for users. So if I have a Gini index equal to 0 for users, what I'm saying is that, okay, they all have the same length in terms of interaction with the system. And of course, we can also consider variance. And with the variance, the variance of ratings is a measure that tells us how many controversial items are in the datasets, meaning that how many items we have for which we can have a very positive and a very negative feedback. Okay, so for which then the variance is quite high. This is another interesting characteristic for the dataset. And then we have all the datasets that we can have if we look at the data under a graph lens. And then if we look at the topological characteristics of the data. So of course we can have the node degree. We have this clustering coefficient, which tells us the connectivity level of nodes of the same type within the graph. So it tells us the connectivity level of users or the connectivity level of items. And we can also have what we call this the degree assortativity, which measures the activity level similarity, and that can be reported also in a graphical way. Okay, so when we select dataset characteristics are very useful when we want to analyze and distinguish datasets from each other, because we say, okay, I'm selecting this dataset with these characteristics, and after the splitting, I'm having after this pre-processing, I'm having this result. So also benchmarking the dataset itself is something that we need to do. And based on all these elements that I presented so far, and I'm going to close, we developed a data rec. Okay, data rec is a Python library that covers all the elements that I've just described. So it focuses on the first two steps of the recommendation pipelines, and it focuses on the dataset part and on the processing part of the data. So it fosters integration, evaluation, and the reproducibility of the approaches, and it is also, we were very we really wanted to create something that was easy to use, and so that's why also we had simplicity in mind when we developed the data rec. Data rec has these 5 main components. Of course, a data model, a processing module and splitting module, a module for interoperability with other recommender system frameworks, and a module for reproducibility. With data rec, you can inject many different kind of data. You can have tabular data, you can have inline data, you can have JSON data, but you can also develop your own class to to process some raw data that are not considered in the current implementation of DataRec. The core class of the DataRec library is the DataRec object that is built on Pandas data frame. And of course, building on Pandas data frame, we are also fostering and enhancing the integrability of DataRec in other frameworks. With DataRec, you can consider all the data characteristics that we considered before. So the number of users, the number of items, number of transactions, space size, shape, density, Gini index, Gini user, and everything else. So you have data, you have metrics, and you have the reproducible pipelines all together. Within DataRec, we also have recommendation datasets, standard recommendation datasets, which are built into the system. So you can automatically download them, the original version. We can trace them, you can version them, you can do everything you should do with these datasets. Of course, you can do all the pre-processing steps that we showed before, and you can easily connect DataRec with the most famous recommendation framework that we have right now. So with Clay, RS, with Cornac, DaisyRec, Elliott, Lenskit, RecBall, Recorus, Recommenders, and RecPack. When a DataRec is run, it automatically records all transformation. So it keeps a complete history of everything that has been done on the data. Okay, so since the very first step when you download the data, when you select the data set, up to the final step when you say, okay, this is my final process data set, you can use it with your recommendation framework. Everything is recorded completely. So you can double check, you can see again everything, and this of course is something that is in the also in this case to favor reproducibility of the approaches that we use, and everything can be exported as a YAML configuration, such that if you want to reproduce exactly all the steps, then you have this YAML file, and then you can again use this YAML file to run again the same experiments. Okay, so just to conclude, a few take-home messages after this this discussion. So recommender systems are becoming more and more complex systems. So when you have a complex system, what happens is that a slight variation in one of the stages of these systems may change drastically the behavior of the overall system. So, and that's why we need to be very careful when we consider each step in the recommendation pipeline. And specifically, we need to be very careful since the very beginning. So since the selection of the dataset, and when we process the dataset that is then used to train the model, to compute recommendation, and to evaluate the proposed approach. Unfortunately, all these elements referring to the first two steps are still underestimated tasks in the training pipeline. But I hope that after this discussion, we will take care more to this, especially since we have DataRec, and we have a tool that can help us in managing these steps in a simple and reproducible way. Thank you very much. I know that I'm a bit out of time, but if you have questions, I'll be very glad to answer your questions.
Thank you very much. It's very interesting. So any question from the audience?
Yes, I have a question.
Yes.
Can you hear me?
Sure.
Yeah.
Yes. First of all, thank you for your presentation. I like it because I also work on I'm also working on recommender systems, and my question is related to I had the pleasure to take part of to the recommender system summer school that was held in Vienna this September. And one of the hottest topic was about the clarity of the works. And as you claimed with DataRec, there is a problem of standardization regarding the preprocessing. And my question was about, do you think that it can be possible to standardize also the fine-tuning? Because another problem that was exposed was that a lot of works that were presented to the recommender system conference claimed to reach the state-of-art performances, but then when a study that was conducted went to reproduce the work, they didn't reach their performances, and a simple matrix factorization was able to outperform that model.
Yes.
So do you think that this can be possible to standardize also the fine-tuning, or I don't know?
We have to. We have to. You know, the short answer is we have to. And in this respect, when I was program chair of Rexis in 2023, one of the first thing that I proposed was that of identifying the main frameworks that we have in the recommender system community, and to say, okay, let's try to use only these frameworks, also because these frameworks, most of them, they have a quite clear pipeline in the training phase, because you are talking about the training phase, right? So also in the training phase, they have also this clear representation on the way you tune hyperparameters and everything else. And for example, in my lab, we also developed Elliot, and Elliot follows exactly the same idea of DataRec. So you have a YAML file that tells you exactly what you do with your training phase. So exactly for each hyperparameter, what is the value that has been used, and so on and so forth. Everything is in a declarative way. So my long answer to your question is that if we want to avoid that many papers published in our scientific community are actually useless because we cannot actually compare to them, we do need to adopt standard tools that describe what we are actually doing. Okay, this is a starting point. Of course, at a certain point we need to say, okay, right now we have almost I don't know how many, that there are more than 10 frameworks. At a certain point, we are going hopefully to converge to 3-4 of this, but we say, okay, this is our standard framework. This is the way we want to describe this processes, and let's go for it. And this is the way that we need to refer. These are the tools that we need to refer to if we want to be reproducible.
Thank you very much.
Okay, I hope that this answers your question.
Yes, thank you.
Thank you very much. Any other question from the audience? I have one small curiosity, because with Luca, we are working also on context-aware recommender system, and especially in situation-aware recommender system.
Yeah.
So first, one practical question: do you think that DataRec could be useful also if we consider contextual data together with the data regarding the items, or we need to expand something? What do you think?
Okay. Well, as when you consider also contextual data, or let's call them side data, okay? So you do not consider just collaborative information, but you consider also side data. Then also in that case, there is a lot of room to do something that is more standard and more reproducible also in this case. But you know, also for this, in my lab we developed a framework that is named Ducho, D-U-C-H-O. Ducho has been conceived to manage multimodal data as side information in recommendation. Okay, and in that case, with Ducho, you can manage and you can process textual, audio. You can have videos. You can have images and everything else. And also in that case, the pipeline is very well structured. It is also in that case is, as you know, as much as we could, it is very declarative. So also in that case, you can use Ducho if you want to do that.
Yes, in fact, when you showed at the beginning of your presentation the slides with the multimodal data,
yeah, exactly,
I thought that one is our context. So we are working in that case. And with Luca, we are still thinking which is the best phase of the recommenders which you can inject to the context, because you can do this in the pre-processing, as you suggested, but also in the model or also as a post-processing. So after the recommendation, you can. The problem also in this case is regarding the dataset, because in addition to what you said in the presentation, there is also a lack of contextual dataset, so dataset with context information. You need to adapt, so you can consider sometimes the time of the day, or you need to make some assumptions, but probably we need to create a dataset that consider also the contextual information, because it's not so easy to find this kind of dataset.
Yeah. As for the way you can put together collaborative and side information, there is I don't remember the name of the author right now. But anyway, there is a seminal paper. If you drop me a line, I can send you the paper. There is a seminal paper describing exactly all the different ways you can combine these elements together. Well, of course, you can have as a pre-processing, a pre-filtering, as a post-filtering. You can inject together. You can combine. You can, there are basically 7 different approaches that you can use, that you can adopt, and based on the domain, you can select what is the best for you.
Yeah, thank you.
You're very welcome.
Okay, any other question? Okay, if not, I think we can close the lecture here. So thank you very much, Professor Noia. So we will keep in touch.
Thank you very much. Thank you. Thank you.
Thank you also to all of you that joined us, and see you to the next lectures. I think it will be next year. So also a very Merry Christmas and a Happy New Year to all of you. Bye-bye.
Bye-bye. Bye. Ciao.
Thank you.
Ciao.
Ciao Laura.
Ciao Giuseppe, auguri anche a te.
Ciao a tutti.
Ciao,
Magari
ci sentiamo.
ci risentiamo noi anche per organizzare la prossima serie. Ciao, ciao.
Ciao, buona serata.